All right, so I'm currently in AP Microeconomics, regular differential equations, regular Calc 3. I've already finished Calc BC, got a 5 on both my regular AP score and then my AB sub score. Anyway, I like math a lot, and I don't know, I guess people think I'm LARPing, so today I'm going to learn everything I can about stochastic calculus. This is going to be part 1 of a series, and yeah, it's going to be absolutely lit. So the reason I mentioned being an AP Micro is because stochastic calculus is the kind of calculus used in quant firms to make decisions, because as Newton put it, the madness of people is almost incalculable. So being able to understand the patterns in what is essentially patternless, straight noise, it's a skill, and it's a skill I want to learn. My first trig professor, first real math professor I had, actually got his doctorate because I don't know, this is like doctoral thesis. Something about integrating Brownian motion. Let's see if I can find it, actually. I know that y'all can't see my screen, but that's intentional. So the reason I'm turning this into a series is because I actually motion. Let's just look up his name. Google Scholar. All right, let's do it. I feel like Google. Okay, stochastic differential equations driven by colored noise. Let's see this. Stemmen, Karsten. Let's look at the author details. I swear he did one about oh, I don't know. This is so weird. But yeah, I believe it was 80 pages. Let me pull that up for y'all. So yeah, let's see what I look like. Copy, paste reference. All right, bet. So yeah, y'all can see that it was about stochastic differential equations driven by colored noise. So I'm not really sure what colored noise is either, and I'm pretty sure I'm going to learn that. I know that noise is essentially just like random data. In terms of like audible noise, we have white noise, which I believe is just every single frequency. Brown noise, which is like majority lower frequencies. Pink noise, it's like there are different colored kinds of noises, so I'm pretty sure the colors just like the distribution of data, like it's still random as a whole. I don't know, dude. But yeah, we're gonna find it out. So again, this is a series. I tried to learn it with Claude. Claude has like a learn feature, but Claude is actually kind of a terrible teacher. So we're gonna learn it through this textbook by the American Mathematical Society. Shout out Miss Stadler. She has a lot of AMS like posters and stuff in the AP Calc BC room. And then we also have OneNote open. This is everything that Claude gave me, so we're just actually going to delete all that. Actually, let's delete all this. And then the title. Yeah. So first course in stochastic calculus. This is the one that Claude recommended. Scroll. Yada yada yada. Can I do 2-page view? Sweet. Oh, why is this page bigger than the other? Interesting. Okay. Preface. Advanced undergraduate students in mathematics. Okay. So I did all of those things except for probability. I don't even know if this is like legible on stream. Let me pull up my stream. View your channel. So I did all. Is this legible? Close the chat. Yeah, I'm pretty sure the page bigger. This advanced. Yeah, this is very much legible. We're good. So today's undergraduate might not be versed in analysis. Was that not a requirement anymore? Why did it do that to me? What page was I on? 2-page view. I'm opening this in Adobe Acrobat. This is BS. God, stop opening on that monitor, bro. Oh. Yeah, exit, dipshit. First course in stochastic calculus. Basic notions of probability. Okay, so probability theory provides a framework to study random experiments, i.e., where the exact outcome cannot be predicted accurately. Okay, yeah, that checks out. Okay. See if we can make that bigger. Wacom Center, mapping, display 2, yeah. All right, bet. So, yeah, it's just randomness, pretty much. Roll of a die, coin tosses. Okay, theoretical framework of random experiment is as follows. All possible outcomes is denoted by this. So like a die, for example. Terrible. We have that shit going on. Let's draw 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4. I don't even know if that's like accurate. I don't even know if a die is made like that. But yeah, so I guess this, since it's a set, is 1, 2, 3, 4, 5, 6. The outcome of a random experiment is represented by an element lowercase omega of that. I'm gonna draw that over here. I'm just gonna move this shit over. Y element, and then this is outcome. So this is what we got, and what we got has to be a part of all the possible outcomes, right? Blah 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 blah. So an event is a subset of Yeah, okay. Empty set are an event can be described by either enumerating all the elements contained in the subset or by giving the properties that characterize the elements of the subset. Okay. Generating an ordered pair of zeros and ones. Yeah, that checks out. You know, if you wanted a pair of zeros and ones that, like, you know, where order matters, like, yeah, okay. To quantify the randomness in a random experiment, I need some music or some, dude. Like, I'm sorry. Like, stream is gonna be mad boring. Ample base. Let's hear this. Whoa, dude, what the hell? I guess we need to drag on like Fruity Limiter or something and then just turn it off. Detect tempo 88 embedded set is 88. All right. Damn, is that even being picked up by OBS? No. Okay, no, it's not. Okay. All right. I think that's a bit loud. Alright. Yeah. Alright. Let's save that to my streaming. Alright. Alright. Sorry guys, I'm kinda Okay, well, knowing that that's working smoothly, I feel a lot more comfortable. Again, sorry about the delay. Yeah. All right, now that that's done, so to quantify the randomness in a random experiment, that is the set of outcomes whose... Whoa, what? Oh, we need the notion of probability on the sample space. So the probability of omega. So yeah. So we have a function p that gives us the probability of an outcome. Yeah, for pretty much any event. And then obviously if it's a completely random ordered pair of zeros and ones, like that would be 1/4. That's why that is. Since there are 4 outcomes in the sample space, this is the equiprobability on the sample space. Yep. Probability on a general sample space, omega is defined as follows. So probability p is a function on events of omega with the following properties. For any event, so probability all right, bet. So the probability for any event has to be between 0 and 1, so it's either 0% likely or 100% likely. Why is this thing looping weird? I bet. Okay. So yeah, additivity, if all of these things are an infinite sequence of events that are mutually exclusive, so they're, you know, essentially if one thing happens, the other cannot happen, then the probabilities are additive. So for example, rolling a 1 on a die, P1 equals 1 6, P6 equals 1 6. Those are mutually exclusive. If you roll a 1, you cannot simultaneously roll a 6 on, you know, one single die. Thus the probability of running one or the other, P1 6, or I don't know. I mean, I guess if we do a set, we wouldn't have to use the union. I'm not sure which notation you'd use, but you know what? It's chill. Okay. The probability of A is defined by number A. So the cardinality of set A over the cardinality of that. Well, this is kind of like what I was saying. So if we had like this subset A equals 1 and 6, the cardinality of A is 2. And then the cardinality of omega for a die, or the amount of possible events there are, is 6. And 2 6 equals 1/3. So that's what we got earlier. Okay, so 2 events A and B are mutually exclusive, then PA plus PB. For any event A, PA to the C. What is PA to the C? Equals 1 minus PA. Like the probability that A doesn't happen, because that is 1 minus the probability of some event in the set of events A happening. Fuck, dude, I don't know. Yeah, I guess we could just that's just the probability of A not happening. For any events A, B, the probability of A and or B equals the probability of A plus the probability of B minus both of them. Okay, so this is why that is A, and then let's have X, and then we have B, and then we have Y. So terrible drawing, by the way, but you know, it's chill, it's whatever. So this is A, B, A, Y, B, X, X, Y. So we can tell the probability of A here is 1/2. PA equals 1/2. The probability of B here equals 1/2, but the probability of A or / and B, you know, of getting one or the other, not necessarily both, but necessarily neither, is 3/4. 3/4, because they're not mutually exclusive. You can have A and B, you don't have to pick between one or the other. So PA is 1/2, 1/2 plus 1/2, and then PA union, or not union, A and B. I'm not sure what you'd call that, like a combined set, mutual set. I don't know I don't know the lingo for that one. The probability that you get both of them is 1/4 minus equals, so that's 1/4. So 1/2 plus 1/2 minus 1/4 equals 3/4. So that's just algebraically how to get to that conclusion. Might be able to, but I'm learning stochastic calculus right now. I'm live on YouTube. If you wanna hear my voice but I'm locked in right now. What was I gonna say? Sweet. Yeah, dude. Monotonicity. If A is either a subset or an equally large set to B, the probability of A is, you know, either smaller than or equal to B. I mean, yeah, if you have either less than or the same amount of shit, the probability is going to be less or the same. Bro, this is like, I'm sorry, I'm getting baited. A less elementary, albeit useful property, is the continuity of a probability. What the fuck? So P is a probability on Q. A1, A2, A3 is an infinite sequence of increasing events. Okay. Then A1, A2, A2 equals the limit as P approaches AN. I mean, yeah, I feel like that's just fucking obvious, no? Because if A1 is a subset or an equally large set as A2, the probability of one or the other happening is just the probability of A2. Right? Like that's just kind of retarded, for lack of a better word. And then for decreasing events, if A1 holds everything, it holds A2, A3, and so on, and they're just getting smaller. If A1 holds if it holds everything, then the probability of I don't know, some event that is in every single, that is in AN for all N, is just the probability of the largest N as N approaches infinity. I like that I actually understand this shit. Like I was getting kind of mad earlier, but like I'm genuinely glad that I understand what the fuck is going on, because like in the tensor calculus book, I spent more time on Google and Claude than I did in the actual fucking tensor textbook. Like this is one of the first textbooks I've read that is not only legible, that might just be because I actually took my meds today. Not only is it legible, it's like, I don't know, like I actually understand what the fuck is going on, and I love it. I'm pretty sure this is just all of AP Stat. AP Stat is so dumb. I'm sorry. I'm not sure how that shit counts as a math class, because so much of it is just a fucking social science. Like so much of that bullshit is actual social science. Like, I don't know, bro. I feel like I don't know, like if you're challenging yourself by trying to take a math class and you hate math and you have like math related trauma or some bullshit, like kudos to you, but I don't know. Don't compare it to calc though, because there are kids at my school saying it's like calc for humanities students. No, it's not. No, it's not. The standard distribution equation we got from the Gaussian integral. Yeah, no. Oh my god, I'm going hard. Pouring up a 4 and it hit like what heart? Oh my god, I'm going on. But I can't shake you, no, you live in my head. Empty place for you, girl, and I still want you instead. Why I gotta beg for something real, never free. For all y'all saying I use auto-tune, there's proof that I do not use There's proof that I don't use auto-tune. I mean, you could just say I have a wide range. Or something, I guess. Holy tangent, what the fuck? Lock in. Okay. Is this proof for the remark? No, the remark is just context. What the fuck am I talking about? Wow, okay. I don't know. Continuity for decreasing events follows from the claim for increasing events by taking the complement. What the fuck does the what is the complement? For increasing events is the consequence of the activity of a probability. If this is just a proof for this, I mean, I kind of explained it. Why are we considering B? What is a telescopic sum? What is the backslash doing here, dude? You know what we're gonna do? We're gonna paste this shit into Claude, and we're gonna ask Claude at Grok, is this real? We're gonna paste this shit into Claude. Shh, we don't need that. Okay, so it's just minus the set. Oh, what the fuck? Okay, so the backslash is just minus. Oh, I didn't even need Claude. What the hell? Okay, so this is saying if we add an and then subtract n minus 1, and then we're technically going to add a n plus 1, and then we're going to subtract a n minus 1, which is going to get rid of adding that. So eventually we're just going to hit this because it's going to subtract every n prior to that. So yeah, that's the exact same shit. And because bn equals an, yeah. Okay. If the, total amount of events, if the total possible events is finite or countably infinite, if it can be ordered, then a probability can always be defined on every subset of omega. So if we have an ordered set a probability can be defined on every subset of that ordered set. If not, there are subsets on which the probability cannot be defined. So yeah, ordered set, you can always find the probability of a subset. Unordered set, you might not be able to find some probabilities. Give me a sec. I want to let me scroll. Very, very basic probability work. The probability of some subset of events has to be between 0 and 1. The probabilities of mutually exclusive events are additive. Bro, I'm trying to get the lasso, bro. Bet. And then this is just a different way of finding it. Different way of finding probabilities of mutually exclusive events. PA union B equals PA plus PB minus P The probability for events that aren't mutually exclusive is calculated with that formula. All right. So what's after that? How do I indicate that a set is ordered? Let's actually use Grok this time just for shits and giggles. Is there a symbol to indicate that a set is ordered? 4 and up a 4 and it hit like walk hard. I got Uzi stuck in my head. All right. Ordered set indicates that there exists what about there does not necessarily exist? Let's see. What about a symbol for, quote, there does not necessarily exist, end quote? Yeah, I don't know my symbols well enough, bro. This is embarrassing. Oh my god, I'm going on. I'm trying to write down that given an uncountable, infinitely large set, there does not necessarily exist a probability for every subset. Yo, this thing is like Whisperflow, but way better because it uses your own PC. Oh. So for all x, where the cardinality of x is, you know, is greater than a countable infinity, so P is the set of all probabilities. Not Yeah, I'm gonna say it's possible that there does not exist. Oh wait, so there is a shorthand way to write this. The cardinality. Less than or equal to. All right, perfect. However, if this is uncountably large, then there does not necessarily exist some probability for A, given that A is a subset of omega, i.e. R. That took way too fucking long. Ordered or countably infinite sets have a defined probability for every A. Non-ordered sets, also known as uncountable infinities, do not necessarily have a probability for every subset A. Yeah, dude. All right, well, that's lit. Everything 0 to 1 and consider the uniform probability A over B minus A. If omega, or no, for the reasons laid out in the probability theory to restrict the probability to quote good subsets unquote of the sample space. What the fuck does that mean? Okay, so you just have to essentially build like a consistent theory. Oh wow, we've been doing this shit for about 50 whole minutes now. In this book, measurable sets will simply be called events. Let's denote F, the collection of events of omega on which P is defined. Okay. Because this is less very basic, like we're dealing with, you know, stuff that AP Stats students would probably die after hearing about. Sets. Advanced set theory? I don't know. What is this whole thing? Man, what is this? That's got to be top 5 stickers I've seen as of recent. Talking about some last first day. I'm just shut up. All right, I had to get in the story. Hi. Yeah. Fuck ass mom, bro. Fuck ass mom, bro. Stop fucking talking to me, bro. I'm trying to learn stochastic calculus. Talk to me later, bro. Oh, I'm sorry. I was still locked out. Okay, so essentially we just need to be good at probability enough in order to realize when good subset, or like where good subsets might be, where good subsets might show up. I.e. So F, fancy F, I gotta come up with a better way to write that. Yep, that's good. Squiggle, squiggle, hook, and then line. F is a subset on omega. Where there exists some P. That looks like a stupid J. Nah, it's chill though. I need to learn how to draw it better. It's more like this. It's like a big curve and then like a little. That's good. That's fire. What the hell? I'm moving that and then I'm putting this in there. The fancy F is a set of events where the probability is defined. Okay. Defined. Kind of like domain. Kind of like domain. Kind of like your domain for perfect. All right. What is a power set? If A is an F, then what is this A to the power of C thing? Oh, so if A is in F, like if there is some subset of events A in F, that means they're defined. And the probability of A not happening must also be in F. So for A subset F, as okay, so if you have the probability of A and that's inside of something, the probability of that not happening must also be defined. So yeah, the probability of something happening is defined, then it's in F. The probability of it not happening must also be defined. Thus, it has to be in F. I'm gonna see if I can move that over. As if there exists some PA as the existence of some probability implies the existence of 1 minus PA equals bro, this probability stuff is light. And because there exists some PA, also, I did that wrong. I not only forgot to put the subset symbol, I also did the wrong F. It's a fancy F. Yeah, no, that's fire. That's actually fire. I'm gonna move this down. If there is a probability for A, there is a probability for not A. Thus, every event that's not A must be an event where the probability is defined, and thus, not A is an element of the fancy F. A subset. Sweet. Okay, so random variables and their distributions. A random variable X is a function from a sample space, omega taking values in R. So X is a function. So I don't understand. Is X a part of capital Omega? And then it has a real valued function? Because how is a variable X a function? Huh? Make that make sense. So oh, so omega is the domain, and then X varies depending on the input event and takes a real value. Okay, that makes sense. Okay, so consider example 1.1. An example of random variables is capital X of omega. So we're saying X is a like real numbered function, and it essentially takes on a value that can describe something about a given input. So if we said, you know, X has to be the number of zeros in some input, then if we give it that input, it's going to tell us how many zeros there are. That checks out. Example of random actual BS. Okay. An example of random variables. So I'm not sure what that little arrow means. See, like this shit? What is that? What the fuck is that? Like that leads to? Whatever, we'll figure it out. Why do we call X a random variable when it is actually a function on the sample space? Okay. Oh, so the input of X is random, and that's why we call it a random variable. So it is literally just, it's a function, but its value is random and varies because the input is random. I mean, yeah, that makes sense. It's stochastic calculus. So if we had x of omega, it's not believable enough. Omega, nope. Keeps looking like tits or something. Okay. X of omega. It's real numbered. I'm gonna type that part out. Technically, it is a random variable as the input lowercase omega is random and it varies. As the input lowercase omega is random and x varies. And then we can also say what is that? The issue is like, I don't know what this is. Like, it's for the fork cracking in a hill I walk hard. Oh my god, I'm going on. An example of random variables is xw that gives. I'm just gonna paste that in. Why do we call x a random variable when it's actually a function on the sample space? Well, of a function whose input is an independent variable. Here, since the input of x is random, we call the function a random variable. So yeah, it's not independent because it's dependent, but we are dealing with noise. So we can't say that x is independent because it depends on lowercase omega, but it's also inadequate to call it dependent because omega is completely random, so it's best to call x random as well. We know lowercase omega is random because we are dealing with noise in stochastic calculus. That's okay, so that's fire. Well, let's see here. Let's see what's going on. Let A be some of n in F. See, okay, see, here's the thing. We're dealing with discrete we're dealing with discrete data, so how would we know how to define f given discrete data? That's my question. Like we have literally discrete data. How would we know how to define f? Like, are we going to be given like actual sets that we like drop into Desmos or whatever the fuck? Like, I don't know. More generally, if x is a random variable in the probability space, omega f probability. Because x is effectively random, any function of x also is effectively random. I don't know. I don't know what is happening. Are we saying this? Okay, so A is sum of n in F. So the probability for A is defined. The random variable indicator functions. I'm so confused. I just need to read, bro. If we have a good description of the sample space, then we can build the function for each W as we did in example 1.9. An important example of random variables that we can easily construct is an indicator function. So, so this is essentially just saying, like, is this thing a part of A? And I don't know. For now, if we had like for all W the set of omegas in, or the set of like lowercase omegas in big omega, where 1A equals the set A. Okay, so this is the tricky part. So this is an example, and then this is essentially what we're getting out of it. Every single omega that delivers 1, like the set of all of them, gives us A. Because every single part of A would deliver us 1. Okay. I guess this is a place where piecewise functions matter a lot more. More generally, X is a random variable on the probability space. Modeling some, okay. If G maps R to R and is a continuous function, like Gx equals X squared, for example, then the composition G capital X is also a random variable. I'm not sure what the fuck they mean by reasonable function of X. I think they mean a function of like, you know, like g of x equals 1. Like that's not really a reasonable function. Like that's always going to deliver 1 no matter what the input is. So I don't know, like a function, a real number valued function of capital X, like that would be a reasonable function, or that is a set of reasonable functions for the most part. Yeah, dude. Okay, so for example, if G maps real numbers, okay, did that part. Consider a probability space omega fp modeling some random experiment. If it is often difficult to have precise knowledge of all the outcomes of omega and of the specific function x. If the experiment is elementary, what the fuck, guys? What do we not show how this freaking sounds, what do we? Alright, bet. That should provide, I mean, not necessarily better microphone quality, but I don't know, it's just out of my face more, I guess. I'm not even really sure what this sounds like in comparison. So yeah, this is bound to be lit. Okay, I think I just kind of fucked it up. Yeah. Yeah, this is rough. Well, yeah. Yeah. Oh. I'm gonna be honest, I'm kind of done. I think it's a bit of a lost cause. So I'm gonna go fix my mic. It's been fun. We learned the very basics of probability.